We want to now discuss binomial random variables. Now, binomial random variables have two parameters. So if I say x is a binomial random variable, so there'll be two parameters over here. One is going to be n, the other is going to be p. Now, what is n, what is p? N is the number of trials, because in binomial random variables, we have finite trials, number of trials. And p represents the probability of success, as in binomial random variable, we have a constant probability of success in each trial. So the idea over here is that binomial random variable is used to represent experiments. So we use it in those experiments with finite independent trials. So this is key. We have to be careful about what sort of experiments can we use it in. With finite independent trials. This is the first condition. You need to have a finite number of independent trials, and n represents that number. So it's finite independent trials. Each has two outcomes, right? So you will either have success or you will have failure, each with two outcomes. So you have a finite number of trials, and each trial is only two outcomes. You can either have success with probability p, right? So we can have success with probability p, or failure with probability 1 minus p. So we can only use it in these specific outcomes. And over here, another important part is that this probability of success needs to be constant in each trial. So probability of success needs to be constant in each trial. So these are the three important conditions that we need for an experiment to satisfy, to represent it by binomial. Needs to be constant in each trial, right? So we need a finite number of independent trials, and each trial should have two outcomes. And the probability of success in each trial has to be constant, and that probability of success is denoted by P. So when we use such a binomial, so when we use a random variable to represent such an experiment, then we define this binomial random variable to be the number of successes in n independent number of successes in the n independent trials, now over here success will be defined in terms of whatever we're looking for, right? So it's success is defined in terms of whatever we're looking for. So define in terms of whatever we're looking for. Like for example, okay, before we look at an example, let's just whatever we're looking for. So like we said, now we have in trials, in each trial can either have a success or failure. The way we define a binomial random variable is, it is going to be the number of successes in any independent trials. And successes will be whatever you want to find in a particular question. So this will make more sense when you look at an example. Now, obviously, because the number of successes in n trials could be anything from 0 to n, so the binomial random variable n takes values from 0 to n. Because it's binomial random variable, we know it will take a finite number of values. And a binomial random variable takes values from 0 to n, because either all trials could be successes, which means that x would be n, or it could be that none of the trials are successes, x could be 0, or you could have any number of successes between 0 and n. Let's consider an example. Say you toss a coin 10 times, and when interested in the number of times we get a head. Now we can represent this with a binomial random variable, as we have 10 finite trials and we know each coin toss is independent. So we have finite independent trials and we have two outcomes. We either get a head or we get a tail. And the probability of success is also constant in each trial, because the probability of getting a head in each trial is always 1 by 2. So because this tossing a coin 10 times meets all three conditions, we have finite independent trials, we have two outcomes in each trial, and the probability of success, i.e. probability of getting a head, is constant in each trial. So we can represent this by a binomial random variable, which we will define as the number of heads that we get in 10 trials. And we know the number of heads could take any value from 0 to 10. Either we get a head every time, we don't get any head, or we get a head for a number between 0 to 10. And obviously, if we were interested in the number of tails, then we would define success to be tails. So in that case, we could define the binomial random variable to be the number of tails that we get in 10 trials. So again, success is defined in terms of whatever we're looking for. So now let's look at a couple of more things. First, now let's look at what is a probability mass function of a binomial random variable. So PMF of binomial random variable is of the form. So the PMF of this, we know a PMF basically tells us what the different PMF of a binomial random variable allows us to define the probability of each value it takes. So the probability that this binomial random variable takes a value k is defined as n choose k pk1 minus pn minus k. And this makes a lot of intuitive sense too. Why? Because obviously we're interested in the number. We know what is x. We define x to be the number of successes in n trials. So we're saying we have k successes in n trials. So we have the probability of success to the power k and the probability of failure to the power n minus k. K successes, n minus k failures. And out of those n trials, any k could be successes, and hence we have n choose k. So this formula makes sense as well. And we know, okay, the expected value of a binomial random variable is given to us as NP. So these are just the formulas. And variance of a binomial random variable is NPQ, where Q is the probability of failure, 1 minus P, right? So it's probability of failure. P is the probability of success, 1 Q is the probability of failure because we have just two outcomes, so it's just 1 minus P. So now before we wrap up, let's look at examples of situations where binomial applies. Examples of situations. We just looked at one right now. Examples of situations where a binomial applies. A first classic example could be finite coin tosses, yeah, dice rolls. So just like we talked about, right? Because whenever we have a finite number of coin tosses or dice rolls, we know we automatically have independent trials. Because obviously, whenever you toss a coin or whenever you roll a dice, every trial is independent of the other trial. In the case of coin toss, though, we have clear-cut two outcomes. We either have a head or we have a tail. In the case of dice roll, obviously, we don't have exactly two outcomes. We have six. But say we were interested in the number of fives, then we would define then we would define the getting a 5 on a dice as success and getting anything else as failure. So we could make it into two outcomes, right? Getting a 5 is success and getting anything else is a failure. And so in this way, and obviously the probability of success is constant in each trial in both cases of coin toss and dice roll. And then we have another classic example could be selections, but specifically with replacement. So it has to be selections with replacement, right? So this is, it cannot be without replacement, right? Because in case of selections without replacement, because obviously if you're selecting something with replacement, you have a finite number of items that you're choosing from, and because you're replacing each time, so you have independent trials, and the probability of success remains constant. Because if we had selections without replacement, we cannot apply binomial in that case. In case of selections without replacement, so if you're selecting stuff without replacing it, binomial does not apply, right? So you cannot apply binomial in that case, because in that case you do not have independent trials and you do not have constant probability of success. Does not apply as dependent trials in this case. Why? Because if you are obviously say you have if you have five balls in an event, three are red, two are black. So if you choose one red ball, you don't replace it. So the next time you choose a red ball, the probability of getting a red ball will change. So probability of success is not constant. You have dependent trials, so binomial can't apply in selections without replacements. In selections with replacements, you can apply binomial. And third could be an example of a student making random guesses in an MCQ exam. Making random, because obviously when you're making random guesses, the probability of getting a right answer is going to be the same in MCQ exam. So just obviously key is you're making random guesses in this. So these are examples of situations where we can apply a binomial random variable.